Hello and welcome to Cashmatics. This is the third video in a series of videos I'm doing on complex numbers, and this is where things really start getting serious. And what we're going to be looking at today is what an Argand diagram is, how to represent numbers on an Argand diagram, how to calculate the modulus and argument of a complex number, and how to switch between what's called the modulus and argument form and the form you've been seeing up till now. You're really going to need to concentrate on this, so clear your minds of all the clutter. Go and grab yourself some paper and a pen and let's get started. The first thing I'm going to explain is what an Argand diagram is. Now, if you remember from the last two videos, a complex number is made up of two bits. It's got a real part and an imaginary part. So you can't actually show it on a one-dimensional number line. You need a two-dimensional space to show it because it's got two parts to it. So let's say we've got the number 3 plus 2i. Now the way we show it is very much like we would show coordinates. So we got the real part over here. So I'd go across to 3. So the real part is 3 and the imaginary part is 2i. So I need to go up to 2i. So that number there, that position there, is 3 plus 2i. And the way to represent it in an Argand diagram is to draw a line from the origin to that point. Now, I've not really drawn that very well, but hopefully you understand what I'm trying to say. So any complex number, so let's say z is equal to a plus bi, can be represented using the vector ab, and that vector is from the origin. So let's just say we have z equals something like 4 minus 5i. So I'd use the vector 4 minus 5, so I'll go 4 across and minus 5, so it'd be somewhere down here, and I would draw a line from there to there. So that's that number represented on the Argand diagram. Or if I had something like z equals, let's say minus 4 plus 3i, I'd use the vector minus 4, 3, and I go across to minus 4 and up to 3, so that's the point there. And that's that number represented on the Argand diagram. So it's quite straightforward. It's exactly like you'd plot coordinates. And the good thing about it is you can actually use some coordinate geometry to solve some of the problems that we'll encounter with the complex numbers. So that's what an Argand diagram is. It's really basic. It's just like coordinates. Now the next thing we're going to look at is what the modulus and argument of a complex number is. So let's say we've got a complex number z equals 2 plus 3i. I'm just going to plot that on the Argand diagram. Now you'll see there's no scale here, and this is how I normally sketch my Argand diagram. So 2 across 3 up, so something like that. So there you go, and that is 2 across and 3 up. Now the modulus of a complex number basically just tells you how big that complex number is. So this complex number goes from here to here, so I just need to work out that length. It's quite straightforward. It is just Pythagoras. So the modulus of z, which I write with two vertical lines either side of z, would equal the square root of 2 squared plus 3 squared, which would be root 13. Okay. Now don't worry about the signs of these numbers here. So for example, if I said z is equal to minus 4 minus 3i. Okay, so minus 4 minus 3i would be down in this quadrant somewhere, so it'd be over here. So that would be minus 4 and minus 3. The modulus of z would equal 3 squared plus 4 squared, all square rooted. Okay, so 4 squared plus 3 squared, square root that, and you get 5. So that's how you work out the modulus of a complex number. It just tells you how big the number is. The argument of a complex number is to do with its angular position, and we measure these angles using radians. And if you're not familiar with radians, or you've forgotten about radians, I suggest you watch my video on introducing radians, which will explain what they are, and it'll just refresh your memory a little bit. Now we first of all need to work out the position 0 on this Argand diagram. So 0 radians would be over here, and if I want to get to this position here, I can go clockwise to go that way, or I can go anti-clockwise and go that way. So any numbers which appear in these top two quadrants, so this is the first second, third, and fourth quadrant. Okay, so any numbers which appear in the first two quadrants, we measure between 0 and pi degrees. Okay, so this here would be pi over 2, and anything we measure in the bottom two quadrants, we go in the negative direction. We go anti-clockwise, so that would be minus pi over 2, and this would be minus pi radians. So that's the first thing you need to understand. That's the normal convention for complex numbers, and we always measure from this point 0. So the angle I'd need to measure for this first complex number here is this angle here. So that's the angle I'd need to calculate. And for the next complex number, because I'm going down into this third quadrant, I would need to know what this angle over here is. Now the first one's quite straightforward. The angle is just, I can just use normal trig to work out that angle, and it would be the inverse tan. So let's just call this theta. Okay, so theta would be the inverse tan of 3 over 2, which equals 0.983 radians. Okay, and the way we express this is the modulus of z is equal to root 13, and we worked that out before, and the argument of z, which we write arg z, would equal 0.983 radians. Now if I was doing this number here, so z equals minus 4 minus 3i, we've already worked out what the modulus is. The modulus we've worked out is 5. Now in order for me to work out what the argument is, I can't really do it with this obtuse angle straight away. Okay, I need to work out what this acute angle here is. So I'm just going to call that angle phi for now. Okay, so I would work out what that is. So that would be the inverse tan. Now what would it be? It'd be 3 over 4, which equals 0.644 radians. And from there I need to work out what this obtuse angle here is. So if you think about it, I'm not worrying about the signs just yet. The angle from this position all the way to here is pi. Okay, although it's negative pi, I'm not worrying about the negative for now. So I just need to take off 0.644 radians from pi radians. Pi take away 0.644. Now I've got the exact answer still stored in my calculator, so what I'm going to do is just work out what, well, I wouldn't say exact, but you know, the whole decimal is on my calculator. So I'm going to do pi take away the answer, and I get 2.498. So 2.498 radians, which means the argument of z is equal to minus, because I'm going around the other way, minus 2.498 radians. And I'll do one more example from scratch so you can see how I do it. So let's just say z is equal to minus 5 plus 3i. So first of all, the modulus of z, and that would equal the square root of 5 squared plus 3 squared, which gives me root 34. And for the argument, I draw myself an Argand diagram, find the position, so minus 5, 3, somewhere over here. Okay, so minus 5, 3. I'm just going to mark this angle on, because that's what I'm going to calculate first, but the angle that's my argument is this one here. Remember, 0 is over here, that's pi over 2, and that's pi. So let's just work out what that is. So that would be equal to the inverse tan of 3/5, which is equal to 0.540 radians, and the angle I'm after is equal to pi take away 0.540, which is equal to 2.601 radians. Okay, so that's this angle here which I've just worked out. So that means the argument of z is 2.601 radians. Moving on then, we're going to look at how to express a complex number using the modulus and argument form. before we do that, we need some background information. So let's just have a look at the coordinate axes together with these graphs of the sine, cosine, and tangent. I want to put something on this axis for you. So I've got a general point xy. So just think of it as a normal coordinate axis. Okay, I've got a general point xy, and I've got an angle here which is theta, and a line which goes directly to that coordinate. And that line has got a length z. So think of this z as my complex number, so which is what we've been doing before. So imagine that was a complex number on an Argand diagram. Now, the position of this can be expressed using trigonometry instead. So if you think about trigonometry, cos theta would be x over z, so adjacent over hypotenuse. Sine theta would be y over z, which is the opposite over hypotenuse. So if I was to rearrange this, I would get x equals z cos theta, and y is equal to z sine theta, which means the general coordinate xy can be expressed as z cos theta, z sine theta. So instead of me writing xy, I can write this instead. Now, if you compare that to a complex number would be a plus bi. Okay, so that would be a normal complex number, but you could plot that using the coordinates ab, which means I could express this complex number as z cos theta plus b, so that's my y coordinate, which would be z sine theta multiplied by I. And the way we express this in complex numbers is z cos theta plus I sine theta, and the z is in fact the modulus of z, okay, because z would be the length of this line. So that's how we can apply coordinates to complex numbers, and we can write them in what's called modulus and argument form. The modulus would be this, okay, so this is the modulus, and the argument is the angle it makes. Now you might be wondering why I've got these graphs drawn here. It's because the angles work themselves out quite nicely. So if the angle is acute, so between 0 and pi over 2, you can see that between 0 and pi over 2, both the x coordinate and the y coordinate are positive. So the x coordinate comes from here. So between 0 and pi over 2, you can see it's positive. Okay, this green bit here indicates it's positive, and the y coordinate comes from sine theta, which you can see is also positive. When it comes to the second quadrant, the x coordinate is negative and the y coordinate is still positive. So the x coordinate comes from the cosine of theta. So we can see here, look, between pi over 2 and pi, it's negative, but sine theta is still positive, so that's the y coordinate. In the third quadrant, now remember we measured these angles between 0 and minus pi, so let's have a look over here. The x coordinate between minus pi and minus pi over 2 is still negative, which is what it is over here, and the y coordinate, which comes from the sine, is also negative. And over in the fourth quadrant, the x coordinate would be positive, so between 0 and minus pi over 2, and the y coordinate would be negative, which is between 0 and minus pi over 2. So hopefully you can see that from these graphs together with these axes. So the general form of a complex number when it's written in argument, so when it's written in modulus and argument form, would be the modulus of z brackets cos theta plus I sine theta. And in the next section I'll show you how to do the whole thing from scratch. So let's have a look at this example. What I'm going to do here is express this number using the modulus and argument form. So z equals 7 plus 5i, and the first thing I tend to do is just plot it on the Argand diagram. So 7 across, 5 up, so somewhere like that. Okay. Mark on the angle. Now that's the angle I actually do want. That is the actual argument. So I'm just going to label it theta. So that there would be 7, and that there would be 5. So the first thing I'll do after that is work out the modulus of z. So z would equal, so the modulus of z would be 7 squared plus 5 squared, and take the square root of that, which gives me root 74. And the argument of z would equal the inverse tan of 5/7, which is 0.620 radians. So Z can be expressed as, remember it's modulus, so it's in this form. Okay, in that form there. So it would be the modulus of Z, which is root 74, open brackets, cos 0.620 plus I sine 0.620. Okay, second example, Z equals 1 minus root 3 I. So let's just plot that first. So 1 across minus root 3, so somewhere down here. Okay, so that would be 1, and that would be minus root 3. And let's put on the argument, it's over here. Okay, that's the argument I need. Now remember, that's going to be a negative angle. I'll work out what it is as a positive angle first and then just stick a negative sign in front of it. So let's do the modulus first. That would be the square root of 1 squared plus root 3 squared, which just gives me 2. And let me just label this angle theta for now. Okay, so theta would equal the inverse tan of root 3 over 1. So if you notice, I'm ignoring the fact that it's negative. I'm just working out how big the angle is. I'll sort out the negative and positive afterwards. And that would give me 3, so it's one of these nice angles, pi over 3 radians. Therefore, Z can be expressed as, remember it's the modulus first, so it would be 2 cos pi over 3 plus, it would be minus pi over 3 because we're going the other way, plus I sine minus pi over 3. Right, and one last example on this. Let's say Z is equal to minus 2 root 3 plus 2i. So let's plot it first. So minus 2, 3, 2i, so somewhere over here is in this quadrant. Don't worry about the scale. As long as you're in the right quadrant, that's the main thing. So minus 2 root 3, and that would be 2. So the angle I'm going to work out first is this one here. That isn't the argument. Okay, the argument is actually this angle. Okay, this one in white, but I'm going to work out the green angle first. Let's work out what the modulus is. So that would be the square root of 2 root 3 squared plus 2 squared, and 2 root 3 squared, that would be 4 times 3, which is 12, plus 4, okay, that gives me 16. So the modulus is 4. This angle here, I'm just going to label it phi, so that would equal the inverse tan of, what would it be, 2 over 2 root 3, which is equal to pi over 6. So this angle here is pi over 6, which means this angle here would be 5 pi over 6, because I've got pi over here, so pi is 6 pi over 6, take away pi over 6 is 5 pi over 6. So my argument is 5 pi over 6. So overall, Z is equal to, remember it's the modulus multiplied by cos 5 pi over 6 plus I sine 5 pi over 6. And one last thing before we finish, what if the number is already in modulus and argument form and we wanted to convert it back into the a plus bi form? It's actually really straightforward. It's probably easier than going the other way. All I need to do is work out what the cos of the angle is. So the cos of pi over 6 is root 3 over 2. It's one of those nice angles. The sine of pi over 6 is a half, which means the number becomes 3 multiplied by root 3 over 2 plus I multiplied by a half. And all I do then is expand the brackets. So it'd be 3 root 3 over 2 plus 3 over 2 I. And it's as simple as that. I'll do one more just to hammer the point home, but it is as straightforward as that. So one last one. So again, I'm just going to work out what the cos of minus 3 pi over 4 is. Okay, so make sure you do pay attention to the negative signs. But if you worked out what this is, you'd find it's minus root 2 over 2, and this actually works out to be minus root 2 over 2 as well. So the whole thing, z is equal to 5 minus root 2 over 2 plus I times minus root 2 over 2, and let's expand that, so it'd be minus 5 root 2 over 2 plus, well, it'd be minus again, 5 root 2 over 2i, and that's all there is to it. So I hope that's helped your understanding of the modulus and the argument of a complex number. And there might be one question you're asking yourself, which is, why do they call it the argument? Okay, it's not because they had a fight or anything like that. I think it's because astronomers used to use argument as a way of measuring the angle to position things in space. So the orbit of planets was measured using arguments. That's the term they used for it. So I think it comes from there. Anyway, that's just a little bit of trivia for you. But anyway, I hope that's helped. And next lesson, what we'll be doing is we'll be going on to looking at how we can multiply two numbers just by using the arguments and the angles, and how we can divide two numbers by just looking at the arguments and the angles. So we don't need to go through the whole process of multiplying and dividing the numbers from scratch. We can actually do it using the arguments and the modulus. But that's for next time. So yeah, goodbye for now.